Okay, as I say in a minute, I'm not guessing. When I say something and I'm not guessing, I am not guessing. Fermilab says these are the two particles that exist, the black fixed and the white point. We found them and then we separated them. When I say that, I am not guessing. These are the two particles we separated. The black separated from the white. They were attached right here as light particles. And they are the same particles that Fermilab has seen. Did not realize they were attached as light because they smash things head on. We're using light to begin with, so we knew they were attached. Now, let's continue on, see if we get some free energy, save the world. How about that? Okay, a lot of people are going to say, oh, I can't understand any of this stuff, electrons and energy and voltages and all that. Don't worry about it, it's very simple. It's just like turning up the temperature at your house. You have a certain amount of energy that it takes to create visible light. You don't get any light unless you use some energy. How much energy do you use? A very small amount. 1.5 to 3.5 electron volts. Well, you know what electrons are. Electricity. Lightning, static, electricity that runs through the wires. That's what electrons do. Now, in order to create them to glow, you have to add energy into them, so you need to add a little extra energy, and that's electron volts. Now, that's only a little tiny amount. So let's say, in order to use a laser, instead of, which creates visible light, same visible light, only it's concentrated. So let's say instead of 1.5 electron volts, we used 1,000,000 electron volts. How about that? We should be able to get some pretty good laser with 1,000,000 electron volts. Would you not agree? Yes, you would agree. Now, so we're blasting laser out of here like crazy. Well, what happens then? If we can create cosmic ray energies, the same output is going to give us trillions of electron volts. So if we started with millions and we ended up with trillions, that would be pretty good increase in energy. And that's what I believe we can do, because we're creating cosmic ray energies at the venturi. All right, one of my favorite sayings is I'm not just guessing, and I'm not just guessing. That is pulsed red laser. Absolutely no question came from the red laser. This is the glowing little particles in the air that are gases or extra electrons that are being concussed by the wave, which is created because of this particle moving forward. So it's a particle-wave duality. And then we accelerated it through the venturi, and then literally separated the black from the white, as you will see. All these things are not known or understood or even allowed during the current model. As I showed you, we can create the black and the white particles that Fermilab has seen, CERN's seen them, everybody's seen them, but they just have them splashed all over. We can actually see them because we started with them. That's as small as it gets, as light. That's it, that's a photon. And then we split those photons at the venturi. And according to the rules of electron volts, when you split from the muon electron showers, they turn into the same as cosmic radiation, exactly the same thing, muons. Muons are cosmic radiation. That is supposedly trillions of volts, and I see no reason to dispute that. There's an enormous amount of energy here, and we started with almost total darkness. Once you hit here, it's boom. All right, I think I made a pretty damn good case for dark matter, and it's one of the most well-known, least understood things in the universe. It says, finding dark matter, one of the highest major goals of physics, said Agard, a nuclear physicist researcher at Gaussian Institute of High Energy Physicals, or IGFAE, the University of Santiago de Compostela in Spain. I have a good friend, Pedro, over there in Spain. Pedro. Speaking, and he had worked for NASA and the European Space Agency, as a matter of fact. Speaking in round numbers, scientists have launched about 100 experiments to try to illuminate what exactly dark matter is. 100 experiments. None has succeeded in 20, 30, 40 years, he said. There was a theory, a very hypothetical idea, that you could observe dark matter with a very particular type of nucleus. You don't need that. Everything there is has dark matter attached to it. This theory centered on what's called dark decay. Well, let me show you something. The only way you can see dark decay is in a nuclear blast. Let's take a look at one. All right, I'm not going to get too deep into this, but it says right here, finding dark matter is one of the major goals of physics. They can't find it. Let me show you what it is. We found it. All right, you see here it is some more. This is the same time frame, 7/19/22. Large Hadron Collider B ramps up the search for dark photons. They just don't have any idea. They know, look, it says it's got to be there because of the way the galaxies dance, but we just don't have a particle to explain it. Yes, we do. I can show you the particle right now. All right, this is how they get the Higgs fields and all of the different particles at CERN. They collide things head on, and when they smash head on, they throw showers this way and that way. They create all these spinning fields, all of these zoo of particles. I mean, they just break them into a bazillion pieces. They hit literally millions of these particles head on to each other. So now you got millions times thousands. I mean, it's just that they're everywhere, so they have no idea. And then they see, like I say, they see chunks, big ones, small ones, little ones. Every single thing there is made on this model. That is electron flood theory. That's how simple it is. These are the two particles make everything. And it's just at certain frequencies and certain quantities. And that's what these periods are. And they seem to be in certain quantities, the vibration becomes stable. That I'm having a hard time with. I got to be perfectly honest with you, but they get all the way down to the smallest one, which is hydrogen, and that's still hydrogen. That's not just one. They'd say hydrogen was just one big proton, right, with one tiny little electron floating around it. No, absolutely not. It's this with one more of these that would like to get into the center, but it says no. We got enough crust. It'll form a crust around it. And this guy will say, I'd like to get in. And I said, no. You can come and try to get in, but you're going to stay 2 angstrom units away, whatever it is. And it may, at some really crazy point, one of these may shoot out of there for some reason, and that's one will jump right in. That'll become the stable core. Now, all you have to do to become from a proton and a neutron is 1 electron difference. It's exactly the weight of 1 electron, because that's what it is. A proton is just a charged particle, a positively charged ball, which they would consider the nucleus of a hydrogen. That's what a proton is. Well, it's not. It's this, 1835. Now, if you take 18, throw one more in there, 1836, now you're neutral. So you're a neutron. And that difference of weight is 0.0005485 atomic mass units. That equals 1 electron. Because if you divide 1, which is the whole hydrogen nucleus, by 1835, that's the number of electrons you have. Add one more, it becomes neutron. All right, the whole takeaway here about the dark matter is it's just attached to the white matter that we could see. This is the stuff that burns, it's electricity, it's light, it's all of the things that we know about, but it's really not matter. It doesn't seem to be. According to Don Lincoln, he says it might have a 0 mass. This is always the same size and always the same weight. None of them change. All the black particles are the same size, the fixed particles. And that's what we see in our light experiments as well. And we don't hit head on with gigantic particles. We take the tiniest light particles and then we split those. So we're way ahead on this game. This tells the whole story right here. Dark matter is one of the most well-known yet least understood things in the universe. We're talking about in the ultra small quantum realm of subatomic particles. That's where I am. I am in the smallest particles there are, because everything that I show, everything is made of the same particles, the two smallest particles, the muon neutrino and electron neutrino. All right, this goes back to, I think, 2014, 2015. I was contacting the Russians and Fermilab about this black hole that they discovered in space, and they couldn't believe it either. They freaked out. They thought they would create lattices and squares inside. Everything would push each other apart, but it didn't. It pushed the extra black particles to the center. They don't mind being on top of themselves. That's what created this white glow around here, and this is what explodes off first thing in a nuclear bomb blast. Because what they do with a nuclear bomb, they force everything in against itself so hard that it all comes out. Well, the first thing that comes out is the white, followed by the black. That's why you have the burning and then the explosion. Alright, this is just as simple as it gets. The first thing that's going to hit this house is the white particles which surround the core of dark particles. You saw the white particles surround the core. They will hit first and just burn the house, but not move the house. Then the dark particles will follow and knock the house into shreds. Now watch this. This is Atom Central. That's the station. Teapot Apple II Q House's atomic bomb effects. Now, what they're going to do is set off the atomic bomb, and like I said, the first particles that hit are the white ones, that are the glowy, burny parts. And watch what happens. Let me set this so that it goes very slowly. I'm going to put it on playback speed of 25%. It's already slow. Here goes, watch this. No, I may stop, and I probably will, because that's just what I do. Boom. What did we just see? I just stopped it. We saw the flash. Every single thing here is burning. Literally everything on the surface is combusting. Watch. Look, he's just smoking and burning. Just that's all that happens. Now, what will happen in a second is, so what I'm saying, these are all the white particles, and they're the burny, glowy, really, they burn. Even all the wires are burning, everything's burning, but nothing's moved. Now comes the black particles, and what they will do is slam the hell out of this, it's exploded, but then everything will come back, because the black core will still be back at where the bomb went off, most of it. And it will want this stuff to come back to it, and it will come back. Watch, so here it goes. Pushing. No pushing. All of a sudden, bam! Alright, don't forget we're running slow. Alright, now watch it turn around and come back. You see it coming back? That's the key. That's what happens in an atomic bomb blast. Alright, so in real world life, what does that mean? Well, what it means is this is the first one to hit, which is the glowy parts that surround the black center, which I'm sure I showed you or will. They're the ones that go first. Then the black ones come. Alright, so the glowy ones, they're gone. Then, and they burn, and they're hot, they burn. When they concuss, they burn. You see that? That's burn. That's what concussion and burn is. And that's what these white particles do. The black ones are the ones that knock the house down. The black ones came afterwards, knocked the house down. All right, see, here's the white ones coming through. Now, that's because we're using light. Where we're bombarding up here, we don't have the same situation as an atomic bomb blast, let me put it that way, because we're not using big particles. We're using light. We're subatomic, and that's what they're talking about now in the ultra tiny quantum range. This doesn't get any tinier than this. And you say, how can I possibly see these particles? The smartphone sensor efficiency for cosmic ray muons. That's what we're looking at. That's what we're seeing is the muons. The black and the white is the muons and electron neutrinos. Case closed. And you can see them. They've been doing this since 2012. Alright, we're creating our own cosmic rays by shooting it through the venturi, creating this splash. Now, I believe it does happen other ways. We can see, obviously, they're looking into space, and they're using cell phones to pick this stuff up. All right, I'm going to try to summarize this, make it easy for you to understand. Muons are produced in our upper atmosphere as our particles up there get collided with by the ionized particles from space, from the sun primarily. Now, here's the conclusion of what muons. This is a couple of types here. Muons are fundamental particles that interact via gravitation, which we know they come to the Earth, electromagnetism, and the weak interaction. So these are the particles that I'm showing, the blacks and the whites. And the muons happen to be the black part. Now, cosmic muons are the ones that come in and they slam into these and they break the apart in the atmosphere. They are produced when primary cosmic rays, which is the blast ray, interact with Earth's atmosphere, just particles roaming around, and smash them into bits. That's cosmic muons. Muon flux and energy is affected by atmospheric conditions. It depends how many particles are in the air, how much is hitting us at the same time, all of that stuff. And they say muons are beneficial to modern scientific research. Well, we have to understand they are the product of what we would consider an electron. The one side is an electron neutrino, and the other side is a muon neutrino. But the muon is the weight. That's the heavy part. That's the gravitation. Okay, I'd like to have them just talk to me. Would be very nice. Okay, I'd like to speak with somebody at the Department of Energy, but I've never gotten an audience. Now, they're talking about muons at Fermilab, and I tried to contact them. They won't respond. As they say that the muons are 207 times heavier, which means they have that much more energy. Einstein's E equals mc squared is basically energy equals mass. Mass is how heavy the damn thing is, or how hard it hits, let me put it that way. Because something that weighs a pound can do 1,000 pounds worth of damage if it's going 1,000 miles an hour. All right, something worth a pound, it can do a pound of damage if it's just dropped to the floor. So it's all about impact value. And we shot it through the venturi, and the impact value we got is just a gigantic explosion which separated the particles, which gives us every bit of that energy plus way more. If it's correct, the electron volt chart I just showed you, or will. All right, don't forget, remember this. This is so simple and solid state. I mean, there's nothing to it, what I'm talking about, if it works. It's a laser and a receiver with just a funnel for forcing the particles to explode. And then you take that energy and you put it into your batteries or whatever. You only need a little small amount of batteries because it's going to continuously keep doing this. It will use some of its energy and it will recycle the rest. I think I showed you something before that you got like 200 times more energy than your laser's using. So you should be just continuously shooting out energy. Now, you might want some batteries in a car or something, a bunch of batteries. I don't know. So you can do anything you want. But if you could carry this into the woods, you just plug your stuff into it and do anything you want. Pump water for fires and, lights for planting, for plants. And, energy rules everything. If you don't have energy, you're in trouble. And right now, we are in trouble. And these wars and all this business is terrible. And I think a lot of it is because of vying for resources. And it's tough to share when you're freezing. That's the problem. And to come this winter, there's going to be a lot of people freezing over there and hungry, and it's not going to be nice. All right, my friends, I don't know if you noticed, but the world is screwed lately. If I am correct, and we can get free energy, which we very well might be able to do, and I'll show you the research we did on this, and it's by splitting these particles, which are the nucleus of every atom is not a bunch of big protons. This would be a proton. It's all these little particles together. We've split them. When you split them, you can increase the energetic value exponentially, it says. Okay, let me just explain to you right now. The whole point of this is to get us out of the situation we're right in now and hopefully be able to get some free energy. And this is how we're going to do it right now. I'm going to show you that from the research we've done, I feel that we can get an increase of energy, basically free energy. Okay, this is a shocker, but outside of mainstream, there's been a new device developed that creates what's called the Warren effect. And it literally separates the electron neutrino from the muon neutrinos. And when you do that, they say you can increase the value of the energy at least 207 times. Let's start to look at it. If we could do this, we can get out of the problem we're in right now. We're never going to have enough energy to go around ever if we keep doing what we're doing. And with these wars and all these things, absolute nightmare. We need free energy, and I think we can get it. Okay, just so that I sort of ball it up in one big ball, that's the dark matter right there. That's where all the weight is. This is what knocks the house down. This burns and has no volume, and that's basically what Don Lincoln of Fermi Lab says. He says it's a point particle, just like an abstract, and this is a fixed particle that never changes. That's exactly what we found. That is precisely what we found in our experiments back at that same time. And this is it. This is a photon, which makes 2 electrons. These 2 particles together are electrons. We always thought they were just a glowy part, which made electricity and burn people and all that stuff. No. They all have a dark side attached to them, and they move around like that. We just never saw it. And because once they get into a ball, the dark is right in the center. You never see it again. The only way we saw it was to be able to look at it with the light using, yes, the smartphones, which are totally capable of doing this job. I just want you to know that all the research supports what I'm saying. Neutrino nucleus, quasi-elastic, 2-particle, 2-hole interactions, which gives us, what I took away from this was that there was excess energy that they found during this interaction. All right, just one last time on this. Remember, again, this is Fermi Lab from back 2013, Don Lincoln, and he's talking about the big black particle and the gushy one, and these are the exact particles we found. Again, in summary, the extended particle, the black one, has a fixed size, never goes any different. It may have a fuzzy edge around it, which it does. The point-like particles are mathematic abstractions with 0 size. But even 0-size particles have an extended field due to the effect of the field surrounding them. So it has to really surround something. But these are the same particles. I mean, literally identical. And we separated them. That is the key. Creating the muons and the electron neutrinos, independent of each other. These create showers. These just stay exactly the way they are. I mean, all I can do is just keep showing and showing and showing until somebody pays attention. We're in trouble. If we can get free energy, and I think we can, by using this extreme amount of reactive energy. We need to harvest it before it gets back together with the black compartment. It separates it. This is a separation of these 2 particles. That is exactly what is required for free energy. All right, so we gain huge amounts of energy and use this little device. Hopefully, if this works, it works. If it doesn't, it doesn't. We're only going to take 60, 90 days tops to know. The laser shoots it through. We've got lasers laying all over the place. We create a little venturi. We tune it just to the right dimensions, and then you will end up getting just what we got. The white comes through and the black doesn't. The black has to go around. Well, does that give us energy? I think so. You can see it. You damn sure can see it. How are we going to harvest it? I don't know. Somebody else is going to have to do that. We got this far, and that's the best I can do for you. No. And again, this is something Rod Warren ran into by accident. We didn't just design this. But why walk away from it just because it was an accident? And if we don't do something quick, this winter is going to be a historic disaster. I'm sorry to tell you, Anybody that's got eyes to see should be seeing this directly in their face right now. Because there's no getting out of this until we figure some way of getting energy, basically for free. Because the more you destroy the Earth, the more you destroy the Earth anyway. So if this works, what a freaking win. I mean, win, 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 win. You could put these in your cars and never stop driving. Put them in airplanes and buses and trains and whatever you want. Run your house. Cabins in the woods. Everywhere you have electricity. In a little lunchbox. All right, I had a lot of people tell me, send this to Trump. Well, you send it to Trump. If he's got some power, let him speak up and see what he gets heard. I'm telling you, I never got a single word heard. If he can get it heard, let's see him get it heard. I mean, think of that, the president that brought us free energy. He'd love that. I mean, who wouldn't? Well, I'm going to tell you, if you wait around for the politicians to do it, we're all going to be dead. I guarantee you, it's going to be the most painful winter in history. You know, that was a stupid thing to say about owning the world, but I say whoever has the energy runs the show. We should all be able to have energy, even the poorest countries. And this should be able to be carried around in like a little lunchbox. I use this just to demonstrate. It's an old Geiger counter. But you could have every type of plug-in available here, AC, DC, anything you want, just by using little conversion devices inside there, and you know, diodes and so forth. And the rest is all solid state, shooting lasers and collecting it. And you only need a couple of inches. And then you could just carry this around. No infrastructure, nothing. Just plug whatever you need in. Any kind of AC, DC, 50, 60 cycles, 120, 220, whatever you want. And you never have to put any energy into it. You can put this in a car and drive forever. You never even have to stop. So this is the key. If we don't do something, we are in so much trouble now. And I don't see any way out unless we jump on this instantaneously and it works. That's the key. I don't know if this will work. I don't know if this will work or not, but I don't see any option.